solid, which is soft, has a low melting point, and does not conduct electricity. Does not conduct electricity is your hint that it is something that is covalent, so it's going to be all non-metals. And the low melting point, you could have thought of ionic, but the fact that it has a low melting point, the ionics have all got high melting points, means it goes on, does not conduct electricity in the molten form, so it definitely couldn't be ionic, it can only be covalent. So we're looking for atoms of a metal, definitely not. Ions, no. Molecules, that's what you get from covalent bonding. A mixed bonding structure, there's no such thing, so C is your answer. Which of the following statements is incorrect? A covalent bond between two atoms is found when the atoms each have partly filled valence orbitals, then they fill up, so that looks reasonable. The bonding electrons must have opposite spin, yes. The electronegativity of all the atoms is very low. No, there is an electronegativity difference that is low. But the electronegativity, if you think about it, something like fluorine and fluorine, that's 4, 0 and 4, 0. So the electronegativity is not low. And electron pairs shared, yes, that is true. So C is your only incorrect answer. It is the electronegativity difference that has to be low. In which of the following compounds is the bond most covalent? So for this we're going to need a periodic table, and we're going to see that all of them are bonded to chlorine, and every time chlorine will have an electronegativity of 3. Now what we want to know, if it's the most covalent, it means I need the smallest electronegativity difference. So basically I'm looking for something else that is closer to 3. Potassium, let's go through them. Potassium 0,8, sodium is 0,9, I'm getting close to 3. Calcium is 1, magnesium is 1,2, I'm getting closer to 3, and beryllium is 1,5. So 1,5 is the closest to 3, so even though that is still considered ionic, it is closer to covalent. Remember I told you there's no clear-cut covalent ionic. It's a bit of a sliding scale, and you have a percentage ionic nature. In which of the following is the covalent bond most polar? Again, I'm going to look at the electronegativities, and this is 2,1 and 2,1, which means it is totally non-polar. Oxygen is also, it's going to be 3,5 and 3,5, so the electronegativity difference is 0. Chlorine is 3,0 and 3,0, the electronegativity difference is 0. So those are all non-polar. So I'm only interested in 2,1 with iodine at 2,5. So that's almost non-polar. I mean, that's a 0,4 difference. And chlorine at 3,0, so that is a 0,9 difference. That is the most polar of all of those. Which of the following formulae is stable for a stable compound must be incorrect? So, if we go over here, we don't know what X is, okay? But X has got a valency of, could have a valency of 3 and bond like that. X could have a valency of 3 and bond like that. X could have a valency of 3 and bond like that. X could have a valency of 3 and bond like that. Because if you think about it, it's X, 1, 2, 3 arms, SO4, 2 arms, SO4, 2 arms. And then we have another X with 1, 2, 3 arms, and SO4 with 2 arms. So that is possible. Let's try and draw out this thing over here. Chlorine has got 1 arm each. And they say there are 2 X's. It's not possible. We don't ever get X with 1.5 arms. So this is the only impossible item. A non-polar covalent bond is formed when? A metal and a non-metal? No, that would be ionic. Atoms of elements with different electronegativities? No, they must have the same electronegativity for a non-polar covalent bond to form. So that's not true. Atoms of 2 different elements in the second period of the periodic table. I mean, that could just as easily be magnesium chloride, and that's definitely not a covalent or non-polar covalent bond. So the second period is going all the way along. No. Ionic, definitely not when you're looking for non-polar covalent. How about atoms of a certain element in group 7? So that would be chlorine bonding to chlorine, or fluorine bonding to fluorine, or bromine bonding to bromine. That is a non-polar covalent bond because there is 0 electronegativity difference, 0 electronegativity difference, 0 electronegativity difference. The valence electron configuration of X is given to me, and it is 3s2, which means that it must be magnesium. And element Y, so that's magnesium, it has a valency of 2, and element Y is over here, it's 3p5, which means it must be chlorine. So I'm going to get MgCl2, and then that would be the same as XY2. So I'm looking for XY2, and that's my answer over there. Which of the following statements with respect to chemical bonding is not true? The bonds are formed because electrons are attracted to by different nuclei. That seems like a true enough thing. There's this force of attraction between the nuclei and the electrons of all the participating atoms. Then the bonds sometimes have both a covalent and ionic character. That is also true. They don't have to be wholly polar or wholly non-polar or wholly ionic. Remember, it's a percentage ionicness. A bond represents a balance between forces of attraction and repulsion. That is also true. The energy of a system is decreased during the forming of a bond. Yes, the whole point of bonding is to lower the energy. Only the magnitude of the charge on the nuclei of atoms has an influence on the strength of the bonds formed. No, there are lots of different factors that have it, not only whether it's positive and how many positives or negatives there are in the nucleus. It's also a link between their electrons and all sorts of things. So having only that is definitely not true. The property of a compound which shows conclusively that it is mainly ionic is, if it has a high melting point, that means it's probably ionic. White color, lots of things are white color, but that doesn't mean it's definitely ionic. And also, something like diamond has the highest melting point of all, and yet it is covalent. So that doesn't conclusively tell me. It's interesting, but it's not conclusive. That's interesting, but not conclusive. You get a crystalline structure in lots of different things. Sometimes you get it in, like water can form crystals called ice. So a crystalline structure doesn't tell me that I've got ionic, because water is covalent. An ionic compound can definitely dissolve in water. Well, not all of them do, and some covalent substances can also dissolve in water, so that's also not true as a conclusive thing. Electrical conductivity only when it melts. That is your definition, or that is a feature of only ionic substances, either when it's melted or dissolved in solution. There was a little mistake in this one. They've muddled the letters up, but anyway, let's go through it. Calcium is element number 20. Fluorine is element number 9. So that's going to become calcium fluoride, and they're going to bond in that way. But Y that's X and that's Y. So it's a metal and a non-metal, so it must be ionic, which means it could only be D and B, and then it's YX2, not XY2. In your own words, with the aid of diagrams, explain covalent bonding. Covalent bonding is the sharing of electrons between two nonmetals. And you could have drawn a picture for that. Ionic bonding is the transfer of electrons from a metal to a nonmetal. And ions attract in lattice. And finally, metallic bonding is metals lose electrons to form kernels, positive kernels, and a sea of delocalized electrons. Metals are good conductors of electricity. Explain this fact referring to the metallic bond. You need to say that the electrons are delocalized and free to move if there is a potential difference. In terms of the electronegativity scale, state whether the following bonds are non-polar covalent, polar covalent, or ionic. So my first one is chlorine and chlorine, so it's 3,5, 3,5. That would be non-polar, and it's two nonmetals, so it's covalent. Hydrogen and chlorine is covalent again because it's two nonmetals. Bromine and chlorine is covalent again because it is two nonmetals. Potassium and chlorine is ionic because it's a metal and a nonmetal. And sulfur and chlorine is covalent because it is a metal and, two nonmetals. When I've got the identical electronegativity, it's going to be polar, at least nonpolar, and polar when I've got different electronegativities. An ionic, by definition, is always polar, but that's a polar covalent. Atom X has a single electron in its outer energy level, and Y has 6 valence electrons. What type of bond? If it's got one electron, that must be a metal. If it's got 6 valence electrons, it must be a nonmetal. So therefore, a metal and a nonmetal must be ionic. And let's draw this. X has got one electron over there, and Y has got 6. And we're going to move that one over there, and we're going to move that one over there, and we're going to have 2x plus and a y like that with a double negative charge, minus 2. In your own words, using an analogy of your own, explain the concept of an electronegativity. You might have used the tug of war idea, but you somehow need to get the tendency of an atom to attract a shared electron pair in a bond, or a bonding electron pair. Use Lewis dot notation to illustrate the bonds in the following elements. So you're first going to have potassium with one valence electron, and it's going to transfer to fluorine, and you're going to have K plus and F minus. Don't forget to show all of those steps. Magnesium has 2 valence electrons, iodine has 7. Magnesium sends its electron to iodine. There are 2 iodines required, so it's 2 iodides and 1 Mg2+. Let's try another one. Calcium has got 2 valence electrons, sulfur has got 6. So the calcium is going to send its electrons over. You're going to get Ca2+, and you're going to have sulfur like with 2 minus charge. Lithium and oxygen. Lithium has got 1 valence electron, oxygen has got 6. That 1 electron goes across. That one goes across. I'm left with 2 Li pluses and O2 minus. In all of those cases, you had a metal plus a nonmetal, so they were all ionic. Now let's look at some covalence. Hydrogen comes in. Oxygen has got 6 electrons, and the oxygen has got 1. And the hydrogen has got 1. They share a pair, and you're left with that. And then nitrogen and nitrogen, I know how it's going to come out looking. It's 2 nonmetals. They've got 5 valence electrons. They're going to share 3 pairs, and we're going to land up with nitrogen and nitrogen like that. Why is a molten ionic compound a good conductor of electricity? And that is because the ions are free to move. Mercury and molten lead bromide are good conductors of electricity for the same reasons. Criticize this statement. It is not for the same reasons. Mercury uses electrons. It's a metallic lattice, whilst molten lead bromide is a molten ionic lattice, and it is the ions that conduct electricity. Electricity is the movement of charged particles, and therefore the charged particles in mercury are electrons, and the charged particles in lead bromide are ions. Why is it incorrect to speak of a molecule of sodium chloride? Molecules result from the sharing of electrons, whilst in sodium chloride the electrons have been transferred. So sodium chloride is actually made up of unit cells, and it is a ionic lattice. And that the NaCl is just the ratio of the lattice, 1 sodium to 1 chlorine. It's not actually a molecule. From the below substances, choose one which would be referred to in the following statements. Choose one substance for each statement. So first I need to think about these. Firstly, potassium is a metal. Carbon is a nonmetal. And it's a very fancy nonmetal because it can also be diamond, and it can be graphite. And I think we've discussed the allotropes of carbon before, or it could be Buckminster fullerene, or it could just be coal. Then you've got magnesium chloride, which is ionic because it's a metal and a nonmetal. And carbon tetrafluoride is going to look like this. It's going to look just like methane, where the carbon hybridizes and forms this tetrahedral molecule with 4 fluorines bonded onto it. So let's see. Has polar covalent bonds, but the molecule as a whole is nonpolar. That's this carbon tetrafluoride, CF4. Is able to conduct electricity in the solid and the liquid phase. That has to be a metal, because if it was a solid, the ionic does not, so it has to be potassium. Particles in the solid phase are bound by ionic bonds. That would be your magnesium chloride, because that's your ionic. And finally, bonds between the atoms differ in different allotropes, and we talked about the allotropes of carbon earlier in the year, where there's diamond, graphite, coal, and Buckminster fullerene, and that is going to be slightly different bonds, so carbon is your example.